have a plenary session that is given an award of the recipient of the 2007 Michel Boudart Award. And for that purpose, I'd like to ask Professor Enrique Iglesia to come forth and to do the introduction. Professor.
Good morning, ladies and gentlemen. It is my honor and my privilege to stand here today to recognize two mentors and two friends, two individuals who have marked my career so positively through their examples, their collaborations, and their friendship. The Michel Boudart Award for the advancement of catalysis is sponsored jointly by the North American Catalysis Society and the European Federation of Catalysis Society. It is the first such joint award. It is sponsored by the Haldor Topsoe Company, and it is being given here today for the first time. The official reading of the award says this award recognizes and encourages individual contributions to the elucidation of the mechanism and active sites involved in catalytic phenomena and to the development of new methods or concepts that advance the understanding and or practice of heterogeneous catalysis. It is meant to celebrate the life and the contributions of a remarkable individual. Michel Boudart has made practical and conceptual contributions to catalysis throughout his life and has been one of the brightest guiding lights in our field. This award is presented here again, as I said, for the first time today, and it will be presented also at the EuropaCat meeting in Turku later this summer. We're delighted that Michel and Marina Boudart are able to be here with us today to celebrate this occasion. They're sitting in the front row here, surrounded by many of his and her academic children, many of whom have actually made this award possible. So let me move on now with the matter at hand. This morning, we also recognize that second person, the one receiving this award for the first time. It is fitting that we present this award to an individual whose career in catalysis has also guided the field throughout many years, for more than 3 decades now. Alex Bell, the recipient of this award, is Professor of Chemical Engineering at the University of California at Berkeley. He's a faculty senior scientist at the Lawrence Berkeley National Laboratory. He has received many, many awards. The AICHE has recognized him with the Professional Progress Award, the Wilhelm Award, and the Walker Award. The ACS has recognized him with the Summer Job Award. And this group of individuals in the audience today, the North American Catalysis Society, has recognized his contributions with the Emmett Award and the Burwell Lectureship. Rather than proceeding to describe the many contributions and many interests and broad interest of Alex Bell, I think I would like to instead let him, in his own eloquent words and through the lecture that he will give this morning, tells us exactly what it is that interests him and how broad they are. In the context of the lecture that he proposes to give this morning, which is titled Probing Catalytic Structure Performance Relations Through Studies of Reaction Mechanisms and Kinetics. Congratulations, Alex. The podium is yours.
There we go. So thank you, Enrique, for the introduction. I'd also like to begin by thanking a number of people who made this award possible and with whom this award would not be possible. So first of all, Enrique and Henrik Topsoe, who were the conceivers of this award and who brought together the thinking of the North American Catalysis Society and the European Federation of Catalysis Societies to make this wonderful opportunity to celebrate and honor the career of Michel Boudart. I'd like to thank the Haldor Topsoe Company for being the sponsor of this award. And most importantly, I want to thank Michel, of course, without whom this award would not be possible, for all that he has done in terms of providing leadership for our field, scientific contributions, and being such a perfect and wonderful mentor and example for many generations of students, many of whom are sitting here in the audience. The only thing I can say is that I regret that I didn't have the opportunity to come to Stanford and work with Michel and be a member of the LSAC team. However, I have had the opportunity for many years now to interact with Michel and his wonderful wife, Marina, to travel, see them in many cities, and interact with them socially and otherwise. So thanks to all for the honor to be here and the opportunity to talk about my work. So I've chosen a theme which I thought is going to overlap the interests of Michel Boudart. I'm going to talk about reaction kinetics and how reaction kinetics ties back to the properties of catalysts. And to get us started, I just wanted to begin with a couple of quotes here. We'll use this button. A couple of quotes here from books to which Michel has contributed. The first is his own book with Diego Maria Dassou, published in 1984, in which Michel says, to understand the activity of the catalytic act at the molecular level, it is necessary, the necessary information is the turnover frequency and its variation with process variables. This is the first important statement. We can't understand catalysis until we understand kinetics. However, he then goes on in the introduction to say that the reputation of chemical kinetics is unfortunately tarnished slightly because kinetic data will usually remain insufficient, meaning if you only put together the kinetics from kind of an intuitive understanding of catalysis, this is not sufficient. And what has to be introduced here is a bolstering by spectroscopic data that define the composition and structure of the catalyst and all intermediates involved in the various elementary steps. And then 10 years later, not in his own book, but in the preface or foreword to a book by Jim Domesic and his colleagues at Wisconsin on microkinetics, Michel holds forth and says that the rate equation is useful in reactor design, but of very limited use in catalyst design. In other words, we need to have, again, other inputs. But the microkinetics of a catalysis proposes a reverse approach, feed to a new age black box, the modern computer, rate constants of elementary steps of catalytic cycle, and then obtain not only the reaction rate and selectivity, but information on each step. So you can see the advancement in thinking that has happened in this 10-year period. I've tried to extend this logic to the following bullet points here, that today what you can say is that kinetic analysis provides you not only an understanding of how reaction conditions affect the rate and product selectivity of a catalytic reaction, and they give you insights that allow you to elucidate which elementary steps control product selectivity and product activity. But we have gone even further today through the aid of the computer and, more importantly, the software that we put into the computer, and in particular our ability to do quantum calculations, that we can now provide ab initio calculations of rate coefficients, so we can think in advance, even in some cases, of doing an experiment, so that we can deduce from first principles what the rate expression might look like, and then see whether that comports with experimental observation. So what I'd like to do in the time that I have here is to go through 4 examples. The first one will be a little longer, the remaining ones will be shorter, and talk about illustrations of how you can bring together experimental techniques and theoretical techniques to get a deeper understanding of catalysis. So we'll start first with a piece of work that was done jointly with Enrique Iglesia on the oxidative dehydrogenation of light alkanes on supported vanadium on alumina. We will look at the effects of the cluster size that we have on the support and its effects on the kinetics of ethane and propane oxidative dehydrogenation. Then we will look at the dynamics of vanadium reduction And what we'll show you is that you need not only steady state data, but transient response data if you really want to take apart the overall kinetics. The second example comes from more recent work on N2O decomposition, where we have used theory to get insights into the mechanism and kinetics of N2O decomposition, the effects of the nuclearity of the active center. I show you two examples here, and then the effects of water and NO on these kinetics, and interpret all of this from first principles. The last two examples are shown here. We'll talk about recent work we've done on the oxidation of methane to formaldehyde on isolated molybdate units. There has been a lively debate about the structure of these units. I'll show you ultimately that this cartoon is most representative of that structure. We'll talk about the mechanism of formaldehyde formation and the kinetics, therefore. And then we'll move on to the last example, in which things will be more qualitative and less quantitative. And I'll show you how one can use an understanding, a qualitative understanding of mechanism to develop catalyst improvements for the case of methanol synthesis from synthesis gas. And we'll look at this non-traditional catalyst that involves copper on the surface of a solid oxide that involves cerium and zirconium. So let's proceed to the first example, oxidative dehydrogenation of light alkanes. And I'll be going back and forth between talking about propane and ethane, but the chemistries are very similar and the kinetics are essentially identical. So the reaction we want to carry out is shown here. Take propane, oxygen, make the olefin, water. Life complicates you. Mother Nature complicates matter by introducing two more reactions, the combustion of the olefin and also the direct combustion of the alkane. But for today, we're going to focus only on the desired reaction, which is reaction 1 over here, the oxidative dehydrogenation. And we're going to ask about how the structure of the dispersed vanadium affects this first rate coefficient. So we have prepared vanadium on alumina catalysts using a variety of sources. And what we find is that as we vary the loading of vanadium onto the alumina, the structure evolves in a systematic fashion. So that at very low loadings, here we see evidence for isolated vanadate species. As you go to higher loadings, you get polyvanidates. These are two-dimensional structures that look like strings and eventually like sheets. At the end of this, you can make a monolayer of vanadium, and immediately you start growing three-dimensional structures that have the characteristics of V2O5 nanocrystallites. So notice that the loadings are expressed in units of vanadium atoms per square nanometer. So below 2, you have monovanidates. Above 2, polyvanidates. And above 7 or so, you begin to form crystals. And we ask whether this has any impact on catalysis. And I show you here that it very definitely does. Propane in green, ethane in blue. This is the oxidative dehydrogenation, the rate of forming the olefin per unit of vanadium on the left. We'll look at that first. And what you see is that if you start with low loadings where you principally have monovanidates, and you go to higher loadings where you approach a monolayer of polyvanadate on the alumina surface, the activity per vanadium increases by a factor of 4 in both cases. And then it reaches a peak, and after that, the site-specific activity begins to decline. And this is the area where you start to form three-dimensional structures, and we can explain this very simply by looking at the areal-based rate, or so the rate based on the area of the catalyst, and you find that here again it rises, and then it plateaus, and it even incorporates the points here and here for bulk vanadium, which is not supported. So we see that the activity increases to the point where we now have a monolayer, and after that you get no further increase because you're only putting more vanadium on, but it's inaccessible. Now, we wanted to understand why the rate changes as we change the loading. And so one of the tools that gives you some insight is UV, ultraviolet, visible spectroscopy. And this has been practiced in our laboratory in situ. Here's a little cartoon of a cell, a little bit of catalyst here. Photons come in, they're scattered over this, off this catalyst pellet, and then out for analysis. And what we see is this kind of spectrum. And if you extrapolate the linear portion here back to 0, you get what is called the energy band gap, or the energy absorption energy over here. And that provides you a measure of the transfer or ease of transferring electrons from oxygen, the HOMO orbitals, to vanadium in the LUMO orbitals. So it's a measure of how easy it is to cross this band gap. Now the question is, how does this relate to catalysis? I'll show you that here. Here is the absorption edge energy. Here is the surface density. And you can see there's a systematic decline in that energy band gap. So if you go to the monovanidates, they have a high band gap. V2O5 at the other end has a band gap that is lower. It's about 2 electron volts. And then if you cross-plot the data from here and from the previous slide, you can look at the rate of, in this case, protein formation versus the band edge energy shown as a declining quantity. And you have here a semi-logarithmic plot and a straight line on such a plot. So what it infers just empirically is the smaller the band gap over here, the smaller the edge energy, absorption edge energy, the higher the activity. And in separate experiments, we've shown that this also correlates with an enhanced ease of reduction, or facility for reduction. So to get even further insight and to ask why is there this relationship, what we've done is to begin thinking about the chemistry here. And this is shown in cartoon form. In this case, we're looking at ethane as the example. Some sort of reversible physisorption over here, a very weak adsorption to get the ethane, the alkane onto the surface. Then a difficult step in which we transfer this hydrogen to one of these vanadyl groups to make an OH and an alkoxide here. And then this is the rate-limiting step, we believe. And then you remove a second hydrogen very rapidly, and you go around the cycle. I just want to focus on this piece of the cycle at the moment. So you see that the first interaction, as we conceive of it, is involving a transfer of a hydrogen from this weakly adsorbed alkane. So here's that bit of the cartoon again, and showing the critical bond-breaking step. And so why should there be a correlation between the activity and the band edge energy? And our interpretation is that the more basic or the easier it is to reduce this vanadium center by transferring an electron up here, the easier it will be to pluck one of the hydrogens off the catalyst surface. And as a way of validating that intuition, we have done density functional calculations here of bringing propane, in this case, up to a little cluster representing part of the polyvanadate. And what we find is that, as one might expect, the weakest bond is the CH in the methylene unit. It transfers first to the vanadyl, and across the gap here, and then eventually, excuse me, that proton ends up on the second vanadyl, and what we have here is an isopropoxide group attached to vanadium. And that it is the CH bond of the the methylene group that is transferred is also indicated by isotopic labeling studies, in which we compare the behavior of a perhydrogenated structure to one involving deuterium at the ends. There's no kinetic isotope effect here, saying that changing from deuterium to hydrogen has no effect on the catalysis, but if we label the center carbon atom with deuterium versus hydrogen, then we see a normal kinetic isotope effect. Things go faster with the hydrogenated reactant, which is indicative then that transfer of a hydrogen atom is kinetically important. So we take this and now we extend the mechanism. So we have the transfer of the second hydrogen to release the olefin. We get 2 hydroxides. They condense to give us a reduced center and release water. And then we have the rapid reoxidation. And at this point, we assume that this reversible step is at equilibrium. and this is the rate limiting step. This one is also irreversible, and that this step involving water is reversible at equilibrium, and that reoxidation is very rapid. So if you put these pieces together, you get a closed form rate expression, which I'm showing you in the box over here. It's first order in the numerator in ethane, and in the denominator, if the water partial pressure is low, you have nothing but a unity here. As the water partial pressure builds up, you build up an inverse dependence on water and a more complicated dependence on both ethane and oxygen. Does this work? Yes, it does. Here's what is called a parity plot. It shows you have near perfect agreement between experiment and this theoretical representation. But the only thing you can extract from the fitting the rate expression to the data is this rate coefficient, or product of a rate coefficient for the rate limiting step and the equilibrium constant. You can't find out anything about the rate of reoxidation, which is captured in this rate coefficient K5. So we wanted to get further insight into this. We really wanted to tear apart all of the chemistry here. So we now want to look at this reoxidation step and ask, how could we get a handle on that? Well, to see what we did, you have to understand that there's another change that happens. There's a change that happens here in the UV visible spectrum when the catalyst is under reaction conditions. We see an increase in the absorption in this pre-edge region where you have E to D electron transitions. And the higher we do, the more we do a reduction, the greater we see the change here in this absorption pre-edge feature. In fact, we can do some intentional reduction and look at the change in that pre-edge feature. And you see there's a linear correlation, and this correlation applies to various catalysts with various amounts of vanadium on their surface. Now, it turns out that in the working catalyst, we're working just in this corner, which extrapolates to 0. So how do we take advantage of this? So I mentioned earlier that you have to do transient response experiments if you want to get all the details. So let me guide you through the various catalysts. The first one, again, is our experimental setup. And now, on the inlet side, instead of working always at steady state, what we're going to do is, with time here, on this axis, work at a fixed oxygen partial pressure, and first a fixed concentration of the alkane, in this case propane, for about 300 seconds. Watch what happens, let things come to steady state, and then we'll do a series of jumps where we increase incrementally the partial pressure of the reductant for 300 seconds, then do it again and again and again. And what we're monitoring is the change in this pre-edge absorbance as a function of time. Now, if you do an analysis of what is going on, you discover that the principal thing that is changing is the concentration of reduced sites, and it can be represented by this differential rate equation over here, which has a number of parameters. It has this epsilon 4, which is a ratio of rate coefficients and equilibrium constant. It has K1 times K2, which is the effective ODH rate coefficient. And it has a constant over here. It just depends on the selectivity of the catalyst. But fortunately, this constant, or this parameter, doesn't change as a function of the experiment. So here's, in black, or in blue, I can't tell from here, the experimental data. It's the one that has the noise on it, outlining. And we can fit this differential equation by adjusting the parameters to give the trajectory shown by the smoother curve. And so by this means, you can extract not only this ratio, but now you can isolate from that ratio the product of the equilibrium constant for the alkane absorption times the rate coefficient for the rate limiting step. And when you put all of this together, I'm going to turn to this side now, you discover some interesting things. First of all, from using UV visible spectroscopy, you get this product, which is the effective or apparent rate coefficient for oxidative dehydrogenation, and it's going up with the loading of the catalyst expressed in units of vanadium per square nanometer. And it's essentially the same at least in the same order of magnitude as what you would have measured from steady state kinetics. So that's satisfying because these are two independent ways of looking at the overall rate of reaction. But in addition now, we can extract the rate coefficient for the rate of reoxidation of the catalyst. And notice that this factor here of 10 to the 5th multiplies these numbers here in the table. So the teaching here is that not only can we get an independent check on the rate coefficient for the formation of the olefin from using spectroscopy, but we can also now isolate the rate coefficient for reoxidation. And these rate coefficients differ by a factor of 10 to the 4th to 10 to the 5th. So in fact, we confirm the notion that reoxidation is very rapid. We also can find out by taking the ratio of these numbers here, the fraction of sites which are truly active. This measures the real activity, this measures the apparent activity, because we count all the vanadiums. And by this means, we discovered that something between 60 and 70%, only 60 to 70% of the total number of sites are really active. So this first illustration, I said this is the longer one, shows you how by using multiple experimental techniques, one can dig deeper and deeper into the kinetics of a complicated reaction and look in this case at both the reduction and the oxidation parts of the cycle and get a full picture. My second example is chosen to show you that if you apply modern techniques of quantum chemistry, notions of transition state theory, ideas about reaction mechanism, that you can get a lot of detailed insight into this simple reaction of N2O decomposition on the catalyst iron ZSM5. So I summarize here what we know already, that is one of the more efficient catalysts for this reaction. Experimental studies show that the kinetics are very simple. They're first order in the reactant, and that you can extract an apparent rate coefficient with a pre-exponential and activation energy. Where the interesting points come is that if you look at the experimental literature, there's a broad diversity of numbers that you'll find for the pre-exponential factor and the activation energy. The activation energy is spread out over 30 kilocalories per mole from very good experimentalists, so there's an issue of what's going on. And then there are indications in the literature that water inhibits the reaction and NO accelerates it, so they have opposite effects. And the question is, why is this so? And then there's also been lively discussion in the literature about the nuclearity of the active center. Does it have 1 or 2 iron centers? And if it has 2 versus 1, how different in activity are these? So we have addressed this from the standpoint of theory with the idea of identifying the mechanism, determining the rate coefficients for all elementary steps, explaining why water inhibits the reaction, but NO accelerates it, explain the reported variation in the pre-exponential factor and activation energy, and look at the role of cluster size over here. So I'm not going to go into the details of how we do this. This would be a talk unto itself. But I will just show you that here is a typical cluster for a single iron atom center. Here's its relationship to the zeolite, ZSM5. And on a larger length scale, here's the network structure of the zeolite itself. And what we're going to look at is how does N2O come in and interact with the center, and how do the products of that interaction then convert ultimately into nitrogen and oxygen. And I'll just say that in order to do this kind of work, you have to look at some maybe 50 to 100 elementary steps. This is a huge amount of computation. Sometimes transition state searches take us days to a week to find one for one elementary reaction. After that, the post-processing of the data is very quick. And what we end up finally with, after you've sorted through all of this work for the case of the Monomeric Center, is shown here in this cartoon. This is the as-synthesized center, and what you would see by XAPS, it's completely inactive, but you dehydrate it, taking total energy uphill 43 kilocalories per mole, you'll get this monooxo structure, and this is active for the decomposition process. If you follow your way through this pink ribbon, that ends up with this interesting structure where you have a dioxo and a monoxo on iron. This is very unstable. That releases the oxygen, takes you back to the beginning. So we have put together this story with the rate coefficients for all of the pieces shown on this network. And as kineticists, then just integrated the equations. And before that, I'll show you the rate expression that you can get. It's consistent with experiment. It's first order N2O. The two more reactions, the combustion of the olefin and also the direct combustion of the alkane. But for today, we're going to focus only on the desired reaction, which is reaction 1 over here, the oxidative dehydrogenation. And we're going to ask about how the structure of the dispersed vanadium affects this first rate coefficient. So we have prepared vanadium on alumina catalysts using a variety of sources. And what we find is that as we vary the loading of vanadium onto the alumina, the structure evolves in a systematic fashion. So that at very low loadings, here we see evidence for isolated vanadate species. As you go to higher loadings, you get polyvanadates. These are two-dimensional structures that look like strings and eventually like sheets. At the end of this, you can make a monolayer of vanadium, and immediately you start growing three-dimensional structures that have the characteristics of V2O5 nanocrystallites. So notice that the loadings are expressed in units of vanadium atoms per square nanometer. So below 2, you have monovanadates. Above 2, polyvanadates, and above 7 or so, you begin to form crystals. And we ask whether this has any impact on catalysis, and I show you here that it very definitely does. Propane in green, ethane in blue. This is the oxidative dehydrogenation, the rate of forming the olefin per unit of vanadium on the left. We'll look at that first. And what you see is that if you start with low loadings where you principally have monovanadates, and you go to higher loadings where you approach a monolayer of polyvanadate on the alumina surface, the activity per vanadium increases by a factor of 4 in both cases. And then it reaches a peak, and after that, the site-specific activity begins to decline. And this is the area where you start to form three-dimensional structures, and we can explain this very simply by looking at the areal-based rate, or so the rate based on the area of the catalyst, and you find that here again it rises, and then it plateaus, and it even incorporates the points here and here for bulk vanadium, which is not supported. So we see that the activity increases to the point where we now have a monolayer, and after that you get no further increase because you're only putting more vanadium on, but it's inaccessible. Now, we wanted to understand why the rate changes as we change the loading. And so one of the tools that gives you some insight is UV, ultraviolet, visible spectroscopy. And this has been practiced in our laboratory in situ. Here's a little cartoon of a cell, a little bit of catalyst here. Photons come in, they're scattered over this, off this catalyst pellet, and then out for analysis. And what we see is this kind of spectrum. And if you extrapolate the linear portion here back to 0, you get what is called the energy band gap, or the energy absorption energy over here. And that provides you a measure of the transfer or ease of transferring electrons from oxygen, the HOMO orbitals, to vanadium in the LUMO orbitals. So it's a measure of how easy it is to cross this band gap. Now the question is, how does this relate to catalysis? I'll show you that here. Here is the absorption edge energy. Here is the surface density. And you can see there's a systematic decline in that energy band gap. So if you go to the monovanadates, they have a high band gap. V2O5 at the other end has a band gap that is lower. It's about 2 electron volts. And then if you cross-plot the data from here and from the previous slide, you can look at the rate of, in this case, propane formation versus the band edge energy shown as a declining quantity. And you have here a semi-logarithmic plot and a straight line on such a plot. So what it infers just empirically is the smaller the band gap over here, the smaller the edge energy, absorption edge energy, the higher the activity. And in separate experiments, we've shown that this also correlates with an enhanced ease of reduction, or facility for reduction. So to get even further insight and to ask why is there this relationship, what we've done is to begin thinking about the chemistry here. And this is shown in cartoon form. In this case, we're looking at ethane as the example, some sort of reversible physisorption over here, a very weak absorption to get the ethane, the alkane onto the surface. Then a difficult step in which we transfer this hydrogen to one of these vanadyl groups to make an OH and an alkoxide here. And then this is the rate limiting step, we believe. And then you remove a second hydrogen very rapidly and you go around the cycle. I just want to focus on this piece of the cycle at the moment. So you see that the first interaction, as we conceive of it, is involving a transfer of a hydrogen from this weakly absorbed alkane. So here's that bit of the cartoon again, and showing the critical bond-breaking step. And so why should there be a correlation between the activity and the band edge energy? And our interpretation is that the more basic or the easier it is to reduce this vanadium center by transferring an electron up here, the easier it will be to pluck one of the hydrogens off the catalyst surface. And as a way of validating that intuition, we have done density functional calculations here of bringing propane, in this case, up to a little cluster representing part of the polyvanadate. And what we find is that, as one might expect, the weakest bond is the CH in the methylene unit. It transfers first to the vanadyl, and across the gap here, and eventually, excuse me, that proton ends up on the second vanadyl, and what we have here is an isopropoxide group attached to vanadium. And that it is the CH bond of the methylene group that is transferred is also indicated by isotopic labeling studies, in which we compare the behavior of a perhydrogenated structure to one involving deuterium at the ends. There's no kinetic isotope effect here, saying that changing from deuterium to hydrogen has no effect on the catalysis. But if we label the center carbon atom with deuterium versus hydrogen, then we see a normal kinetic isotope effect. Things go faster with the hydrogenated reactant, which is indicative then that transfer of a hydrogen atom is kinetically important. So we take this and now we extend the mechanism. So we have the transfer of the second hydrogen to release the olefin. We get two hydroxides. They condense to give us a reduced center and release water. And then we have the rapid reoxidation. And at this point, we assume that this reversible step is at equilibrium. And this is the rate limiting step. This one is also irreversible. And that this step involving water is reversible and at equilibrium. And that reoxidation is very rapid. So if you put these pieces together, you get a closed form rate expression, which I'm showing you in the box over here. It's first order in the numerator in ethane, and in the denominator, if the water partial pressure is low, you have nothing but a unity here. As the water partial pressure builds up, you build up an inverse dependence on water and a more complicated dependence on both ethane and oxygen. Does this work? Yes, it does. Here's what is called a parity plot. It shows you have near perfect agreement between experiment and this theoretical representation. But the only thing you can extract from the fitting the rate expression to the data is this rate coefficient, or product of a rate coefficient for the rate limiting step and the equilibrium constant. You can't find out anything about the rate of reoxidation, which is captured in this rate coefficient K5. So we wanted to get further insight into this. We really wanted to tear apart all of the chemistry here. So we now want to look at this reoxidation step and ask, how could we get a handle on that? Well, to see what we did, you have to understand that there's another change that happens. There's a change that happens here in the UV visible spectrum when the catalyst is under reaction conditions. We see an increase in the absorption in this pre-edge region where you have D to D electron transitions. And the higher we do, the more we do a reduction, the greater we see the change here in this absorption pre-edge feature. In fact, we can do some intentional reduction and look at the change in that pre-edge feature. And you see there's a linear correlation, and this correlation applies to various catalysts with various amounts of vanadium on their surface. Now, it turns out that in the working catalyst, we're working just in this corner, which extrapolates to 0. So how do we take advantage of this? So I mentioned earlier that you have to do transient response experiments if you want to get all the details. So let me guide you through the various panels. The first one, again, is our experimental setup. And now, on the inlet side, instead of working always at steady state, what we're going to do is, with time here, on this axis, work at a fixed oxygen partial pressure, and first a fixed concentration of the alkane, in this case propane, for about 300 seconds. Watch what happens, let things come to steady state, and then we'll do a series of jumps where we increase incrementally the partial pressure of the reductant for 300 seconds, then do it again and again and again. And what we're monitoring is the change in this pre-edge absorbance as a function of time. Now, if you do an analysis of what is going on, you discover that the principal thing that is changing is the concentration of reduced sites, and it can be represented by this differential rate equation over here, which has a number of parameters. It has this epsilon 4, which is a ratio of rate coefficients and equilibrium constant. It has K1 times K2, which is the effective ODH rate coefficient. And it has a constant over here. It just depends on the selectivity of the catalyst. But fortunately, this constant, or this parameter, doesn't change as a function of the experiment. So here's, in black, or in blue, I can't tell from here, the experimental data. It's the one that has the noise on it, outlining. And we can fit this differential equation by adjusting the parameters to give the trajectory